measuring the size of a set by measuring the size of its cover. So an outer measure, this measurement, we want it to be positive, and we want the empty set to have 0 measure. We want it to respect subsets, and we want it to respect unions. So that if I'm doing a countable union, I want the measure of each individual piece to be bigger than the measure of the union. That's monotonicity and countable subadditivity. Let's start easy. R2 going into 0, infinity, because I could measure the whole space, that's infinite. We'll do the naive thing of just say, let's just cover the set by unit squares. So there's R2, and I'll cover it. A is a subset of B, and just measure the size. So I start counting squares. 1, 2, 3. Size 10. B is all of A plus the excess. Another 10. So here's countable subadditivity, is that the union, which is just the size of B, that should be less than if I count up A and B. Yeah, I do want that. Translation invariance is also a desirable trait. This measure doesn't have it though. So let's look at a set A of size 9, fits inside a 3 by 3 square. But if I just move it over a little bit, I'm going to call that A sub t for A translated. That's a 4 by 3, size 12. This is not a desirable trait. So the naive way of deciding how to cover is probably not what we want. Even more of a problem, suppose I have something that's not really area. Well, I can cover it with 1 square, but if I put it along the sides, now it's 2 squares. Well, then if I put it in the crosshairs, now it's 4 squares. This is really not what I want. So let's define an outer measure that has all the nice properties. I'm just counting up unit squares, where the lower left-hand corner is in an index set. The index set will be all the squares whose union cover A. And then I'll label it by the lower left-hand corner. Right? Doesn't matter, you just got to pick something. So this works. This definition, however, has a problem. There's my 3 by 3 set. There's 9. But this also covers A. Well, all I want's the part that actually covers A. I don't want the part that's excess. So how do I say that? How do I get rid of that stuff? I could talk about intersections with A, and it has to be non-empty. Here's a slicker way. Just make the count the smallest. There we go. Everything that doesn't intersect A is automatically discarded. Here's a bigger problem. All our indices are on our graph paper, so they're in integers. This is not translation invariant. We want to be able to move that around. So just put our lower left-hand corner anywhere we want. So there's our set that's 3 by 3. But now if I'm allowed to shift my squares anywhere I want, I may be able to get a more efficient packing. There you go, 8. But if I'm allowed to put the lower left-hand corner anywhere I want, I could also have overlap. This is true. That's fine. So cutting our lower left-hand corners, There's our index set, 8 ordered pairs. Well, here, with this overlap, if I move that square so it doesn't overlap, I should have less numbers of squares that cover it. Maybe I need the overlap, and then I have it. But the infimum will force overlaps to the smallest. One last refinement we want to do. We don't want to limit ourselves to unit squares. Let's change that to rectangles. So now we need a new measurement, v of ij, where ij is going to be a rectangle whose lower left-hand corner is at coordinate ij, but ij are reals, so they can kind of slide where I want to. Put it against the vertical and horizontal measuring sticks, and just measure the size of the rectangle. Vij will define then in the natural way. Base times height, where I is a closed rectangle. Whether it's open or closed doesn't really matter all that much. It's just easier if it's closed. This is the definition of Lebesgue outer measure, which will lead to Lebesgue measure.